Thank you for joining this short introduction to KLEE, which I'm going to give with my KLEE commentator, Martin. KLEE uses a technique called dynamic symbolic execution, which is essentially a technique for automatically exploring multiple paths through a program, reasoning about path feasibility using a constraint solver. You can see dynamic symbolic execution as somewhere between dynamic and static analysis. So for instance, dynamic symbolic execution, or just symbolic execution for short, can reason about all possible values on each path that it explores, something that is typically out of reach of a dynamic analysis. At the same time, symbolic execution can interact with the outside environment, for instance, with system calls and non-instrumented libraries, something that is typically out of reach for a static analysis. Symbolic execution is also a testing technique because it can generate concrete test inputs for all the paths that it explores. And in particular, this means that it can generate actual inputs, triggers any bugs that it discovers. Finally, I want to mention that dynamic symbolic execution can reason about highly complex properties because each path is encoded as a mathematical formula. And this means that it has applications beyond bug finding and test generation. For instance, it has been successfully applied to debugging, vulnerability exploitation, equivalence checking, program repair, and many more. I don't have time to say more about symbolic execution in this short talk, but if you'd like to find out more, I think a good starting point is this review article that I wrote with Kaushik Sen a few years ago for the communications of the ACM. KLEE is a dynamic symbolic execution platform for LLVM bitcode, primarily targeting the C programming language. We first published on KLEE in 2008 together with Daniel Dunbar, who's also the main author of the original KLEE code base, and Dawson Angler. KLEE incorporated the lessons that we had learned from our prior dynamic symbolic execution system called ICSI. So KLEE is quite an old system. In fact, it's over a decade old now. But at the same time, I see it as quite a new system as well, because it has continuously evolved to incorporate both recent research and engineering innovations. Importantly, KLEE is open source. It is available on GitHub under a liberal license. It's primarily developed nowadays in the software reliability group at Imperial College London with me and Martin as maintainers, but with many important contributions from outside our group as well. And we recently released version 2.1 this March. In terms of impact, for instance, the original KLEE paper was elected into the ACM SIGOPS Hall of Fame, which is essentially a test of time award for the paper. And the paper has also received a large number of citations. What I find particularly exciting is that these citations come from many different fields, and here I mention just a few with which I'm more familiar, but there are more, which I think tells you about the applicability and relevance of dynamic symbolic execution and KLEE in particular. We also maintain on the KLEE website, and you can see the URL here, a list of now over 150 papers and systems that use or extend KLEE in many interesting ways. And KLEE has also been used and extended outside of academia by a number of companies, some of which are mentioned on this slide. So now I'm going to pass it to Martin, who's going to tell you about some of the interesting features of KLEE.
Hi, and welcome. My name is Martin. How to get started with KLEE? One way is to download the source code from the GitHub repository and to compile it, or to use one of the precompiled binaries which we provide with Docker. We're currently supporting a variety of different platforms: Linux, FreeBSD, and Mac OS X. KLEE is using the LVM compiler infrastructure, and one of its major building blocks, the LVM intermediate representation, LVM-IR. To test an application, for example, which is written in C or C++, we need to compile that application into LVM-IR. One way to do that is, for example, use the Clang compiler. As KLEE works on LVM-IR, we can also test applications that are written in other languages, as long as there is a compiler which is able to convert those languages into LVM-IR. After we've compiled the application, KLEE can run it and each potential path for this application. For every path, KLEE bit precisely models the memory and its accesses. And using a very efficient object-level copy and write schema, KLEE is able to keep tens of thousands of those paths simultaneously in memory. To direct KLEE to specific parts of the application, the user can use searchers. For example, from a very simple depth-first or breadth-first search, KLEE also provides random searches and more sophisticated coverage-guided searches. KLEE provides different solvers, which can be selected by the user, depending on the different domain the tested application is from. We're currently supporting STP and C3 mainly, and via MetaSMT, also Selector, CVC4, and Yikes is supported. Many applications also need external interaction, and KLEE provides different means to handle this. For example, for the POSIX API, KLEE provides already some models that allow to execute an application without invoking external system calls. Moreover, KLEE also supports different libc implementations. And if needed, KLEE can also handle external library and system calls. But that's not all. KLEE can be easily extended. It provides different interfaces that makes it straightforward to implement new search strategies or combine with existing ones. Similar for solvers. Also, new constraint optimization strategies or caching strategies can be easily implemented and tested using the provided interfaces of KLEE. Besides that, also adding new instructions or how they can be handled is straightforward. The existing POSIX implementation is not complete, but many projects that build on top of KLEE showed how easy it is to extend it. KLEE also supports a variety of different LVM versions, starting from the very old LVM 3.8 to the newest, most recently released version, LVM 10. This allows to combine KLEE with other LVM-based projects that require a specific LVM version. Now some small advertisement. After a very successful first KLEE workshop in 2018, we want to repeat this again and give the opportunity for different KLEE users and developers to meet together, from research and the industry. Therefore, there will be a second International KLEE workshop in April in 2021. And we would be very happy to see you there. Thank you very much for joining us today. And remember to try it out.
Thank you very much, Christian and Martin. I'll keep my fingers crossed that next year it will be possible to attend the workshop in person. Let me stop screen sharing. And with that, we have the opportunity to ask questions to Christian and Martin. There are some here already. I think they were aimed at a different talk. Here we have one that is directly aimed at you. From Tesla Zhang, Penn State University. Do you have some AGC mechanism, term taken from the Python talk earlier, to shrink the execution state? If no, do you think it's going to help?
Right. So I don't remember when the term was introduced, but As Martin already said, KLEE actually one of the main contributions of KLEE is to be able to maintain a large number of states in memory. And in fact, I think that's actually a good question for Martin to add to, because he recently did some work on trying to further increase the amount of sharing in states in KLEE. Martin, do you want to say something about it?
Well, just to keep it quite short. So yes, there are a couple of opportunities to keep, for example, different memory objects kind of shared parts of them or sharing them between states. That makes it quite efficient and reduces the overall memory consumptions quite a lot. But there are also a couple in general. I mean, if you have a couple of states simultaneously in memory, you can share many things, and that makes it quite efficient.
Thank you. The next question that we have is from Manuel Carrasco. He says, thanks for the talk. How does KLEE support concurrency?
Right. So I guess the short answer is that the mainline KLEE does not support concurrency, but there are extensions of KLEE. In particular, I'm thinking now of Cloud9, which added support for p-threads. For instance, and I think there is we do have like an old PR there for that in the mainline as well, but unfortunately we haven't managed to add such support. I think there is much more to do in terms of concurrency testing, but I think that's still in the research realm.
Well, yes. So, and another answer is also, I think, a more recent publication in the CAP 2020 from the guys from Aachen. They also had an extension to KLEE which supports concurrent execution. But at the end, it's straightforward to implement. Also, although it's some work.